Namaskar students. In our previous class, we have studied how the pendulum was oscillating about the mean position with the time interval t by 4 to reach the maximum position t by 4, t by 4, t by 4, and how the phase difference was created between xv and acceleration. Now today we are going to start with few terms. They are undamped SHM, damped SHM, forced oscillation, free oscillation, and resonance. So what do we mean by undamped oscillation? See, the oscillations in which the energy is not decreasing after each oscillation, the total energy remains constant, are undamped oscillation. That means they are not losing the energy, they are not going to stop once they start oscillating. They are oscillating for the, yeah, they're oscillating till the infinity. So when we say undamped oscillations, for example, a wall clock having a pendulum supplied with a battery, it keeps on oscillating with a fixed amplitude and time period. That is undamped oscillation. Now talking about the damped oscillation, the amplitude of the oscillation will keep on decreasing after each oscillation. For example, you guys are on a swing in a garden, and when you are on that particular swing, the amplitude keeps on decreasing if you are not applying any additional force in each oscillation. So that is damped oscillation. In real life, the oscillations that we guys see, which are not sourced or pumped up with some additional force, they are damped oscillation, damped SHM, where the energy in each oscillation will decrease. Now to understand this, we say a container having a fluid, a wall with a spring, and an object which is partially immersed in a fluid. Now when we say partially immersed in a fluid, let's say they are immersed in a fluid, saying it to be the weightless block, weightless spring. Now only the mass m is working on it. Somewhere in the equation, the equilibrium position is there, and we are going to stretch it a bit in a downward direction. So we'll say the force responsible for the SHM is definitely F is equals to minus kx, whereas a force is definitely opposing this SHM. It is going to stop that SHM because air resistance would not have been that prominent. So we have taken damped SHM in a fluid, and I can say if I am having additional force which is making this SHM, this oscillation damped, and this could be a viscous force from the fluid that we have studied in the chapter fluids. If it is a viscous force, can be written as F is equals to minus BV, where I would say B is the damping constant and V is the viscous force acting on this body, which is opposing the motion of the object, and it is producing a damped oscillation. So if we say, zooming out a bit, if we say the amplitude produced in the damped oscillation are going to decrease with each oscillation, almost the same amplitude, then they are going to decrease, and it won't last for a long period of time, whereas undamped SHM will keep the amplitude constant for n number of oscillations. So when we say we have damped SHM, the amplitude is going to get decreased. Reason behind it, a damping force, and this in combination can be written as this can be written as beta F equals to minus kx minus bv, saying force to be m d square x by dt square plus kx plus bv, that will become b velocity is dx by dt equals to 0. This is a particular equation representing the damped SHM. So we can say the solution to the equation: describe the motion of damped oscillation. We are not bothering about it right now. Just understand the terms: undamped SHM, damped SHM. Now, what is the free SHM? Free oscillations means, free oscillation says when an object is oscillating with its natural frequency. Now, every oscillation has some of its natural frequency with which it has the tendency to oscillate about the mean position. If it is oscillating with that particular natural frequency, we would say it is a free oscillation. String of sitar is an example of free oscillation, producing each string producing different sort of sound. Prongs of a tuning fork is also an example of free oscillation, producing its own natural sound on the vibrations. Now, when we say that these oscillations were not maintained because they were getting reduced, the amplitude, the energy was getting reduced after each oscillation, some amount of force is to be applied to keep it moving with the constant amplitude. That particular oscillation will be called now as forced oscillation. So particularly the cell, the battery in a wall clock with a pendulum is providing some amount of energy, some amount of force to that pendulum after each oscillation to keep it moving in the same amplitude. With the same amplitude, the constant motion can be seen, which will be termed as forced oscillation, which is very simple. When you are on a swing and your amplitude gets decreased, for example, I am there with you guys in the garden and I am pushing you from the back after each oscillation to give you some amount of force, keeping your amplitude constant. Now your oscillation will be forced oscillation. Talking about the forced oscillation, the equation of damped SHM can be modified for the forced oscillation, such as the equation m d square x dt square b dx by dt kx, the complete damped SHM would be equal to or responsible because of some force oscillation. So some force is acting. Let's say that force is a restoring damping force independent of time. So we can write it as F naught cos 2 pi nu t, which can be written as cos omega t. So when the equation is equal to a force, now solution of this equation is going to explain the forced oscillations in detail. So when we guys are talking about the forced oscillation, the complete SHM is equal to a force which keeps you moving with a constant amplitude. Now imagine you are on a swing in a garden. A force is applied every time on the maximum amplitude. When you reach at that point, a small amount of force is applied to keep you guys moving with a constant amplitude. Now if that force is applied somewhere in between, it is going to hinder your oscillation. Your maximum amplitude won't be achieved, or somewhere this is not going to keep you moving with the constant amplitude. Your amplitude may vary, or it might show some loss in energy, and because of this forced oscillation, you are definitely not having the fixed amplitude every time. So the applied force has to synchronize with your oscillation ka time period. When this is moving with a fixed time period, this force applied every time is to synchronize with the position when you are on the maximum amplitude. This synchronization, this mixing, this overlapping or matching of the frequency is called resonance. A very simple example. For example, we have FM. We guys say 93.5 FM should be played. Now for 93.4, it is not playing. 93.6, it is not playing. When your device has the frequency 93.5, and your song is floating on that particular frequency bandwidth, when your device ka frequency is matching with the signal frequency, frequencies are matching, this is moving, pushing, again moving, pushing, again moving, pushing, same frequency is matching, this is called a resonance. So I hope it is clear. When frequencies synchronize and they match, this particular thing is called a resonance. In a very simple manner, I have tried to explain you guys without making it very complex. Seeing this particular example, having 4 pendulum tied to a single string, D is given some amount of force to start the oscillation. Let's say it is having its free oscillation. D is having free oscillation. Natural frequency per oscillate. It is doing. Now this oscillations travel through the string to the another pendulum C, B, and A respectively. When it is traveling and these vibrations go till pendulum B, B will also start oscillating. Now having or being of equal length, identical pendulum, B will definitely oscillate with its own natural frequency after getting these frequency because it is same. But we could say D and B will oscillate with the same properties, same time period. They are going to resonate with each other because they are identical. So these two will resonate with each other. Whereas while talking about C and A having different length beta, these are going to show the forced oscillation. These are going to show the example of forced oscillation. They are definitely going to start oscillate with some different frequency, but B and D are going to oscillate with same frequencies. They are going to resonate. This is moving with free oscillation, and they are example of forced oscillation. I hope this much is clear. This particular example that we guys are seeing, beta, the oscillations in which 2 or more bodies oscillate being connected to one another and affect each other are called coupled oscillations, beta. Now they are coupled oscillations. Coming back to the term free oscillations, as someone is asking this in chat. Free oscillation says when they are oscillating with their natural frequency. For example, we have given the natural frequency to D, transferring that frequency to B. So this could be a free oscillation and B is resonating with D. I hope this much is clear. So for now, we have studied major important terms and some properties, characteristic equations of SHM. Now we are going to apply it to find the time period of different systems. The very first and the most important one is simple pendulum. Seeing a simple pendulum oscillating about its mean position, we can say a pendulum of length L is oscillating. So length of the pendulum is given to us L. This mg is acting in the downward direction, forming some angle theta with the vertical. The angle remains same. It will move as mg cos theta, and another force should be in the perpendicular direction component will be mg sin theta. Now the force which is responsible for its SHM is definitely mg sin theta acting on some perpendicular distance. So I can say the torque produced is minus, because this is in the downward direction, opposite to the moment of the displacement, mg sin theta, force into perpendicular distance is torque. The restoring one which is responsible for its SHM, and as the angle is very small, sin theta can be replaced with theta minus mg theta L is torque acting. The restoring torque has its formula as k theta. The restoring force says minus kx. Force becomes torque, k is as it is, x becomes angular displacement theta, which is minus k theta. So I can say m G theta L minus would be equal to K theta. Theta se theta beautiful cutting, minus se minus beautiful cutting. Now we can say the K is equal to mgl. K, the spring constant, spring factor is equals to mgl. I hope this much is clear. First of all, the force responsible for the SHM is clear. Now we have found the value of K. We have already derived the formula for time period. The time period says 2 pi root inertial factor upon the spring factor. It says inertial factor upon spring factor. So when we say inertial factor, inertia of the bob oscillating, I would say inertia is simply mr square. So I can write it as ml square 2 pi root में ml square upon spring factor. Spring factor is said to be mgl as we have calculated. L से L beautiful cutting, M से M will get cancelled out. And this will become T is equals to 2 pi root L by G. This is the time period with which the pendulum bob will oscillate. Is this thing clear? In previous classes, we have studied time period is 2 pi root displacement upon acceleration. So length can be taken up as L and acceleration can be taken as acceleration due to gravity. The formula could also have been used directly, which would be helpful in the competition exams for you guys. I hope it is clear, and that is all for today. We'll start with the cases, some special cases of simple pendulum and other system for which we will try to find out the time period of oscillation. Thank you. Have a nice day.